So very good morning, welcome back viewers. So today we are into the next chapter, chapter 2 of fluid mechanics, fluid pressure and its measurement. So in this module we will be determining the equation for fluid pressure, in fact derive the equation for fluid pressure, and at the end of this chapter the reader should be able to determine the pressure at various locations in a fluid at rest, that is a fluid in static equilibrium, and also you should be able to explain the concept of manometers and apply appropriate equations to determine the pressures. So manometers are the instruments used for measuring pressure in a fluid. So when a fluid is at rest, it cannot sustain any shear force or shear stress, and the only force which acts on the fluid in addition to the self-weight of the fluid is the pressure, the fluid pressure. So in this chapter we will consider the problems of fluid in which the fluid is either at rest, that is complete rest in static equilibrium, or it is moving in such a manner that there is no relative motion between adjacent particles. That is, you treat fluid as a solid, as a rigid body. So if a rigid body moves, there is no relative motion between the particles in a solid. Similarly here, even though there is a relative movement, we assume that the fluid is in continuum and one particle follows the fluid particle and there is no relative motion between the adjacent particles. So in both these cases there will be no shearing stresses in the fluid. So when you assume that the fluid moves like a rigid body, like a solid, then there is no shearing stresses in the fluid. The only forces that develop on the surfaces of the particles will be due to the pressure. So our principal objective is to investigate the fluid pressure and its variation throughout a fluid and the effect of pressure on submerged surfaces. In fact, that we will discuss in the next chapter on fluid statics. The absence of shearing forces, that is the assumption that the shearing forces do not come into play, it very much simplifies the analysis and allows us to obtain relatively simple solutions to many important practical problems. So even when the fluid is in motion, we assume that as there is no relative motion between the adjacent particles, it is assumed, and the entire fluid system moves like a rigid body. So there are no shearing stresses which come into play, and it very much simplifies the analysis and allows us to obtain relatively simple solutions to many important practical problems. So let us first define what is pressure or the intensity of pressure, pressure intensity. So pressure is nothing but a stress quantity. A stress quantity. So how is a stress expressed? Stress is expressed as force divided by area, force per unit area, right? Shear, stress is expressed as force by area. So it is the force exerted per unit area, say per unit surface of the fluid, say for example, or per unit surface of the container which is in contact with the fluid. Suppose let F be the total force, F is the total force which is distributed over an area which is A. Say the total force is uniformly distributed, then the pressure at any point, the pressure is denoted by the letter small p, small alphabet P, then the pressure at any point on the area will be F by A. So F is the total force in newtons, A is the area over which the total force is distributed uniformly, so area has got units meter square. Therefore the pressure will be force divided by area. There is a uniform pressure intensity as the force is uniformly distributed over the area. So you have the pressure intensity having units Newton per meter square, the SI units of force. Suppose you may have a situation wherein the total force is not uniformly distributed over the area on which it is acting. then the pressure P is equal to F by A gives only the average value of the pressure on the area. So when the force F is not uniformly distributed over the area, this expression P is equal to F over A gives only the average value of the pressure on the area. Or in other words, when the force F is not uniformly distributed, the pressure varies from point to point on the area. In such a case, the magnitude of pressure at any point on the area can be obtained by this expression. P is equal to dF over dA. P is equal to dF over dA. So the pressure intensity is not uniform, it is varying from point to point. So dF is what? The infinitesimal force or the force acting on an infinitesimal area dA. So dF is the force acting on an infinitesimal small area dA. So you find the pressure intensity, and if you integrate this one, you will get the pressure force, right, on over the entire area. So SI units of pressure, as we discussed, pressure is expressed in Newton per meter square, it is force per unit area, or pascals. What is pascal? 1 Newton per meter square is 1 pascal. 1 Newton per meter square is 1 pascal. So we all know that a fluid is a substance which is capable of flowing. So when a certain mass of fluid is at rest, that is in static equilibrium, how? By keeping it in a vessel or a container, then the fluid exerts forces against the solid boundary forces. So the fluid comes in contact with the surfaces of the container in which it is kept. So it is exerting a force, that is a pressure force on the solid boundary surfaces. Now let us discuss about the direction in which the fluid at rest exerts force on the surface of the vessel in which it comes in contact. What is the direction of this pressure force which is exerted by the fluid on the surface of the container with which it comes in contact? Now the force is exerted by the fluid always in a direction normal, that is perpendicular to the surface with which it comes in contact. So why? See, the force is exerted by the fluid on the surface with which it comes in contact. In what direction? In a direction normal, perpendicular to it when it. So why? Because the reason is very simple. The fluid is at rest, that is in static equilibrium. It cannot sustain any shear stress, that we have already seen. The shear stress acts parallel to the surface of contact. So therefore the forces will not have any tangential component. Say for example, I have a container in which say a liquid is stored with a free surface. Now, so can you subject say for example, the fluid is at rest, it is in static equilibrium, it is not moving, it is not subject to any shear stress, that is say for example parallel to the surface. So therefore there will not be any deformation in the horizontal direction. So there is no force acting in this direction. There is force acting only in the vertical direction, that is normal to the surface, The fluid pressure, so how it can be defined? As the force exerted by a fluid per unit area of the surface with which it comes in contact in a direction normal to the surface. So this is how the fluid pressure can be defined. So it is nothing but the force exerted by a fluid per unit area of the surface with which it comes in contact. In what direction? In a direction perpendicular to the surface with which it comes in contact. It should be noted that even if you consider an imaginary surface within the fluid body, an imaginary surface, say for example like this, an imaginary surface in dotted lines, the fluid pressure and pressure force acts on the imaginary surface. They are also same as those acting on any real surface. So now let us discuss on the variation of pressure in a fluid mass. So let us consider a liquid, say stored in a vessel with a free surface. Let us consider a small fluid element. within the big mass of fluid, which has a size that is delta x by delta y by delta z. So, delta x, that is the dimension of the fluid element along x direction, delta y along y direction, and delta z along x direction. So, delta x multiplied by delta y multiplied by delta z will give you the volume of the element, volume of the fluid element. In a static mass, there is standing mass of liquid that is at rest, as shown in figure. So, I have blown up the element. So, delta x along the x direction, the dimension, delta y along y direction, and delta z along z direction. So, how the x, y and z, say this is x, this is y, which are mutually perpendicular. That is, xy is in a horizontal plane. This is, say, the origin, then this will be the negative x direction, and this will be the negative y direction, and z direction is in the vertical direction. So, this is plus z and this is minus z. And these three axes are mutually perpendicular. That is, x is perpendicular to y, y is perpendicular to z, and x is perpendicular to z. So, all the three axes x, y, z are mutually perpendicular. Now, the fluid is at rest. So, let us consider the various forces acting on this fluid element. There are two sets of forces. So, the first one is pressure forces on the 6 phases of the fluid element. Now, I have named this fluid element. I have given capital alphabets for the 8 corners of this element. The fluid element has got 8 corners, a rectangular fluid element or a parallelepiped we call. So, O is the midpoint of the fluid element, that is at the center of the element, at the center of the element. O is at the center of the element. So, pressure forces acting on the 6 faces of the element. So, 6 faces, the 6 surfaces of the element, outer surfaces of the element. Then the self weight of the fluid element acting through the center of gravity of the element passing through the center of the element O, that is the midpoint of the fluid element. Now, let the fluid pressure, that is the pressure intensity at the midpoint O, be small p. The pressure intensity, the fluid pressure intensity at the midpoint O be p. Let us assume that the pressure intensity varies from point to point. It is not constant, it is varying from point to point. We assume that it is varying from point to point in the fluid element in all the 3 directions. So, when you move from O to the right or the left in x direction, it varies. When you move from O in front or back of O, it varies. It varies when you go up or down in the z direction, it varies. The midpoint is considered as the origin of these 3 mutually perpendicular axes. That is very important. So, the origin is considered to pass through the midpoint O of the element. Okay. Now, let us determine the expression for the pressure intensity and the pressure force. So, pressure force, how you obtain? So, when you multiply the pressure intensity, which is Newton per meter square, by the surface area on which the pressure intensity is distributed, you will get the pressure force. So, we will determine an expression for the pressure intensity and pressure force in x direction, on the left hand face ABCD. So, I will go back to, say, x direction is, this is x direction. It can be towards right. If it is towards right, it is positive x direction. If it is towards left, In the horizontal direction it is minus x, negative x direction. So you have to consider the normal force or the perpendicular force which is acting on the left face, that is A, B, C, D, as well as the right face E, F, G, H. So A, B, C, D is normal to the x direction, the left face. The right face E, F, G, H is also perpendicular to the x direction. Now you have fluid mass surrounding this fluid element, because you have picked at random a fluid element from within the mass of the fluid. So you will have a pressure force which will act in a direction normal to the surface, that is A, B, C, D, the left face, that is acting in this direction. So we have to get an expression for the pressure intensity on the left face A, B, C, D, and an expression for the pressure intensity on the right face E, F, G, H. Now because it is a small element, fluid element, an elementary parallelepiped, we assume that even though the pressure intensity is varying from point to point, we assume that as the surface area is very, very small considered for the element, we will assume the pressure intensity to be constant over the small area, the surface area. Now let us consider the variation. Now the face ABCD is perpendicular to x direction. The pressure intensity over the face ABCD is along the x direction, is normal to the face, but is it along the x direction. So for computing the magnitude of pressure intensity on face ABCD, we have to consider the variation of pressure intensity in x direction. So as per the sign convention, what is the sign convention? So O is considered as the origin. So right of O it is positive, left of O it is negative. So right of O, that is a positive x direction, left of O, that is negative x direction. Okay. So the pressure intensity at O, say here at O it is P. So in the right, that is towards positive x direction, it is considered to increase, whereas in the negative direction of x it is considered to decrease. So left of O the pressure intensity is considered to decrease, and right of O the pressure intensity is considered to increase. So let the variation of pressure intensity in x direction be referred as dou P over dou x, dou P divided by dou x. So the variation, so we use the partial derivative. Why we are using partial derivative? Because we are considering three directions. So we assume that the pressure varies in all the three directions, mutually perpendicular directions x, y, and z. Now we are considering the variation of pressure only in x direction. Therefore, we are using the partial derivative. We are considering the variation in P with respect to only x direction. So dou P by dou x. So the rate of variation of pressure intensity x direction is represented as dou P over dou x. Now let us, what is the length of the fluid element to the left of the midpoint O? The total length is what? Delta x. The total length is delta x. The total length is delta x. Now to the left of O, O is the midpoint. So to the left of O it is delta x by 2. Here it is delta x by 2. So right to the right of O it is delta x by 2. Therefore, the total variation in pressure intensity over the length delta x by 2 to the left of the point O is a product of rate of variation in pressure intensity in x direction and the length of the fluid element. So it is the variation is dou P over dou x multiplied by delta x by 2 is the total variation in pressure intensity. So now what is the pressure intensity on face ABCD in x direction? It is given by P minus dou P over dou x multiplied by delta x by 2. So why this minus? Because we assume that in the negative direction, that is to the left of O the pressure intensity is decreasing, to the right of O the pressure intensity is increasing. So P minus dou P over dou x delta x by 2. Similarly, on similar lines we can discuss and prove that the pressure intensity acting normal to the face, right face EFGH in negative x direction is given by P plus dou P by dou X delta X by 2. So this is P minus dou P by dou X, dou P into delta X by 2, and this is P plus dou P by dou X, because the pressure variation is positive here on the right side. So, but P plus dou P by dou X, this is the pressure intensity. This is acting in which direction? Negative X direction, whereas this one is acting in positive X direction. So, the direction of the pressure intensity is important, the pressure force is important. Okay, now there the corresponding pressure force on the left hand face ABCD is what? The pressure intensity is P minus dou P over dou X into delta X by 2. This is the pressure intensity on the left face ABCD, which is acting in X direction. So, if you multiply by the area, now what is the area of ABCD? So, ABCD, AD is the dimension along Y axis, that is delta Y, and AB or DC is the dimension along Z axis, that is delta Z. So, delta Y delta Z is the area of the face ABCD. So, this will give you the pressure force acting normal to the left hand face ABCD of the fluid element in what direction? In X direction. This acts in positive X direction. Okay. Similarly, we can prove that the pressure force on the right hand face EFGH, that is normal to the right hand face EFGH, that is acting along negative X direction, is the intensity is this much. This is the intensity, P plus dou P by dou X into delta X by 2 multiplied by the area is delta Y delta Z. So, the right face EFGH has also got the same area delta Y delta Z. So, this will give you the pressure force acting in which direction? In the negative X direction, in the negative X direction. So, now what is the net pressure force in X direction? So, okay, let us now go to the Y direction. We will derive an expression for the pressure intensity as well as pressure force in Y direction on the front face. So, Y direction means this is the Y direction, this is negative Y direction the force, and this force is acting in the positive Y direction. Okay. Now, the front face is ABFE is the front face. The rear face is this one, that is DCGH is the rear face. So, ABFE is normal to Y axis. ABFE is the front face normal to the Y axis. Similarly, the face DCGH is normal to the Y axis, that is the rear face. AB is in the negative Y direction, okay, that is front face, that is below the origin. The pressure intensity is considered to decrease in the negative Y direction, the same logic as we. Similarly, the variation of pressure intensity Y direction is given by dou P over dou Y. So, because we have assumed that the pressure varies in all the three directions. The length of the fluid element in the negative Y direction from the midpoint O is delta Y by 2. So, the face ABFE is located at a distance delta Y by 2 from midpoint O. So, what is the pressure intensity? The pressure intensity is minus P minus dou P by dou Y into delta X by 2 into, sorry, this is delta Y by 2, delta Y by 2, not delta X. Similarly, this is also delta Y, not delta X. So, kindly make this change, there is a typographical error here. So, the phase ABFE is located at a distance delta Y by 2 from point O. The pressure intensity on the phase ABFE normal to Y direction is given by P minus dou P by dou Y delta Y by 2. P minus dou P by dou Y gives you the variation of pressure intensity in Y direction. You have to consider the variation over a distance delta Y by 2 from midpoint O. in the negative x direction. So minus is because of the negative x direction. So this gives you the pressure intensity in normal to the phase ABFE. Similarly, the pressure intensity on the rear phase DCGH is given by this minus will become plus, that's all. It will become plus P plus dou P by dou Y delta Y by 2. So it should be noted that the phase DCGH is normal to y axis and in the y direction. It is considered that the pressure intensity increases in y direction. Okay. Now, so everywhere there is a typographical error, you make that it is delta Y. So the corresponding pressure force on the front face ABFE of the fluid element is what? The product of the pressure intensity on the phase ABFE and the area of the phase. What is the area of the phase ABFE? We will go back to the ABFE. So ABFE. So AB, it is delta Z. BF, it is delta X. So delta X, delta Z is the area. So P minus dou P by dou Y into del Y by 2 multiplied by delta X delta Z. Similarly, pressure force on the rear face DCGH, that is acting normal to the face DCGH, in what direction? This is in negative y direction and this is in positive y direction. This is positive y direction, this is negative y direction. So that will be P plus dou P by dou Y into delta Y by 2 multiplied by delta X delta Z. So we have quantified these two forces. This is P minus dou P by dou Y. So here it is correctly printed, delta Y by 2 multiplied by delta X delta Z, whereas this one will be P plus dou P by dou Y delta Y by 2 multiplied by delta X delta Z is the area. So now on similar lines we have to get the expression for the pressure intensity and pressure force in Z direction on the top phase BCGF and the bottom phase ADHE of the fluid element in Z direction. So when you consider Z direction, that is the vertical direction. So vertical direction you have to consider the two phases, the bottom phase, that is ADHE, ADHE, and then BCGF. BCGF is the top surface. So what is the pressure force acting normal to the top face BCGF in what direction? This is negative Z direction. Then pressure force acting normal to the bottom face ADHE in what direction? In the positive Z direction, this one. So these two, they can be derived on similar discussions. So the pressure intensity at the midpoint is P. So it is decreasing in the negative Z direction, it is increasing in the positive Z direction, that is above O, and below O it is decreasing. So the variation in pressure intensity in Z direction is given as dou P by dou Z. So when you have to find out the pressure intensity at the bottom phase, the distance you have to consider is delta Z by 2. So P minus this will give you the pressure intensity on the bottom phase ADHE. Whereas on the top phase BCGF, it is P plus dou P by dou Z into delta Z by 2. Now the pressure force can be expressed as pressure intensity multiplied by area of the face. So area of the face is what? Area of the bottom face or the top face. Bottom face, say ADHE. AD is the distance along y direction, that is delta Y. DH is the distance along x direction, that is delta X. So delta X delta Y is the area of the bottom face as well as the top face. So delta X delta Y. So P plus dou P by dou Z, delta Z by 2 multiplied by delta X delta Y will give you the pressure force on the top face BCGF that is acting in the negative Z direction. This is negative Z direction because it is acting downward, vertically downward. Then the pressure force on the bottom face ADHE that is acting in the upward direction, that is positive Z direction, positive Z direction. That is P minus dou P by dou Z, delta Z by 2, delta X, delta Y. So we have got expressions for the pressure intensity which is assumed to be uniform on the faces considered, because the face, the area of each phase is very, very small because we are considering an infinitesimal fluid element. So we have got the expressions for pressure intensity on the left face, right face, that is in X direction, then front face and rear face in Y direction, that is normal to these phases in Y direction, and pressure intensity in Z direction, that is acting normal to the bottom face as well as acting normal to the top face. So we have got expressions for these things. Then in addition, we have got the seventh force. So we have got 6 pressure forces on the fluid element. There is one in left face, another normal to the right face, all these pressure forces normal to the faces. Left face, right face, front face, rear face, bottom face and then top face, and these two in X direction. It can be left face, it is positive X direction, right face it is negative X direction, front face it is positive Y direction, right face it is rear face it is negative Y direction, bottom face it is positive Z direction, and top face it is along a negative Z direction, that is vertically downward. So 6 pressure forces we have established the expressions, assuming that the pressure varies in all the 3 directions. Now the 7th force is the self weight of the fluid element. So what is the weight of the fluid element? Now we know that the volume of the fluid element, which we originally mentioned, it is the product of these 3 dimensions, that is dimension along X axis multiplied by dimension along Y axis and multiplied by dimension along Z axis. So delta X is the length along X axis, delta Y is the length along Y direction, delta Z is the length along Z direction. So delta X multiplied by delta Y multiplied by delta Z will give you the volume of the fluid element. Now if you know what is the specific weight of the fluid, so specific weight of the fluid multiplied by volume, delta X, delta Y, delta Z will give you the weight of the fluid element, weight of the fluid element. So how weight, it is a force quantity, that means it has got units Newton. So what is the specific weight? It has got units Newton per meter cube. Volume has got unit meter cube. So meter cube and meter cube get cancelled, you get the force, that is the weight of the fluid element in Newton. So self weight of the fluid element is gamma multiplied by delta X, delta Y, delta Z. Now we have to consider the equilibrium, the static equilibrium of the fluid element which is at rest. Under the influence of these 7 forces, 6 pressure forces and then 1 self weight. That is, for static equilibrium, the algebraic sum of forces on the fluid element in any direction must be 0. The algebraic sum of forces acting on the fluid element in any direction must be 0. That is, sigma Fx should be equal to 0, sigma Fy equal to 0 and sigma Fz equal to 0. What is algebraic sum? Algebraic sum means we have to consider the directions, because whenever I say a force, a vector, force is a vector quantity. So vector, not only the magnitude is important, the direction is also important. So if it is upward, say the force is considered positive. If it is downward, the force is considered negative. If it is towards right, the force is considered positive. If it is towards left, the force is considered negative, that is negative X direction. Similarly, if the force is towards the origin, that is say this is say x direction, this is y direction. So y direction is towards the rear face, and negative y direction is towards the front face, and towards left is negative x direction, towards the right is positive x direction, and vertical upward is z direction, positive x direction, vertical downward is negative z direction. So algebraic sum of forces along x direction is 0. That is sigma fx is equal to 0. So you have to execute this equation. So let us again go back to the diagram. You see. So the 7 forces. How many forces are acting in x direction? Only 2 forces acting in x direction. One is the pressure force acting normal to the face ABCD, that is acting in what direction? In positive x direction. Then the pressure force acting normal to the right face EFGH in what direction? In negative x direction, that is towards left. So these two are the forces acting in x direction. So the force acting on the left face, that is positive, this is positive, P minus dou P by dou x delta x by 2 delta y delta z. The force acting on the right face, that is towards negative direction, therefore I introduce this sign minus, minus, minus. Then this is the pressure force acting on the right face, that is normal to the right face in negative x direction. So this should be equal to 0. So if you simplify this, you will get ultimately, so you can go through these steps, they are self-explanatory, and we will have minus delta x delta y delta z minus the variation in pressure intensity in x direction equal to 0. Now see, I have minus some A into B equal to 0. What is A? A is the volume of the fluid element, delta x delta y delta z. B is what? Dou P by dou x, that is the variation in pressure intensity in x direction. So A into B equal to 0 means either A can be 0 or B can be 0. So one of these two numbers should be 0, but here out of these two quantities, delta x delta y delta z cannot be 0. Why it cannot be 0? Because it represents the volume of the fluid element. The volume of the fluid element cannot be 0. Therefore what must be 0? Therefore dou P by dou x should be equal to 0. Dou P by dou x equal to 0. So that means what? Dou P by dou x equal to 0 means the pressure intensity does not vary in x direction. The pressure intensity does not vary in x direction. The pressure intensity remains uniform, remains the same, say in x direction. It does not vary. So dou P by dou x equal to 0. Now let us consider the y direction. So what is that? The algebraic sum of forces in y direction must be 0. So again let me go back to the diagram. See, y direction, this is one force and this is another force, that is one acting normal to the front face, that is AB FE, and the rear face DC GH. That is this force acting on the front face is along y direction, that is positive y direction, that is along this direction, and this force is in the negative y direction. So this is a negative force and this is a positive force. Okay. So acting on the front face, that is P minus dou P by dou y multiplied by delta y by 2 multiplied by the area, the surface area of the front face, delta x delta z, minus, that is the force acting on the rear face, that is in the negative y direction, therefore minus P plus dou P by dou y delta y by 2 multiplied by delta x delta z equal to 0. So when you simplify, you get minus delta x delta y delta z multiplied by dou P by dou y equal to 0. Delta x delta y delta z cannot be 0 because it represents the volume of the fluid element, therefore dou P by dou y equal to 0. This means what? the pressure intensity does not vary in y direction. So pressure intensity does not vary in y direction too. So it is not varying in x direction, it is not varying in y direction. So it must vary in z direction, is it not? So let us examine. So now let us consider the third mutually perpendicular direction, that is z direction. So sigma f is equal to 0, f z equal to 0. That is the bottom phase and then the top phase. And then in addition, you have got one more force, that is the self weight of the fluid element. So here you have got three forces. So two pressure forces. One acting normal to the bottom phase, another acting normal to the top phase. What is acting normal to the bottom phase is in the upward direction, that is plus z direction, positive z direction. What is acting on the top phase is in the negative z direction, that is vertically downward. Similarly, the self weight of the fluid element is also acting vertically downward through the midpoint, so it is also in the negative z direction. So vertical upward means positive, vertical downward means it is negative. So P minus dou P by dou Z delta Z by 2 delta X delta Y is the pressure force acting normal to the bottom phase. Minus Y minus, this is the pressure force acting on the top phase, normal to the top phase in vertical downward direction, therefore minus. Then minus, Y minus, the self weight of the fluid element is acting vertically downward, so minus equal to 0. So when you simplify this, you get minus delta x delta y delta z multiplied by dou p by dou z, which gives the variation of pressure intensity in z direction, minus the self weight of the fluid element equal to 0. Here delta x delta y delta z, so dou cannot be 0, therefore you get ultimately dou p by dou z is equal to minus gamma. So minus dou p by dou z is equal to gamma, or dou p by dou z is equal to minus gamma. So what you get, dou p by dou z equal to minus gamma. So this is a landmark derivation. So you get dou p by dou x dou p by dou x equal to 0, dou p by dou y equal to 0, dou p by dou z equal to minus gamma. So the pressure intensity varies in z direction, in the vertical direction. It varies. So the pressure intensity at any point in a static mass of fluid does not vary in x and y directions, and it varies only in z direction, vertical direction. How it varies? At a constant rate equal to the self weight of the fluid. Why it is, what is minus gamma? What does minus gamma signifies? So what is z direction? Is it positive z direction means it is vertically upward. Negative z direction means it is vertically downward. Right? This is positive z direction, this is negative z direction. So when I say dou p by dou z, that is elevation. Z represents the elevation. Z represents the elevation. Elevation means you are moving from the bottom to top. So as z increases, so when you go from bottom to top, the pressure of the fluid decreases. At what rate? At a constant rate equal to specific weight of fluid. That is why minus. It is decreasing. So the minus sign signifies that the pressure decreases with increase in elevation at a constant rate equal to specific weight of fluid. So dou p by dou z. So now I am writing this as dp by dz equal to minus gamma. What is dp over dz? How the partial derivative has turned into a total derivative? Because so we assumed initially that the pressure was varying in all the three mutually perpendicular directions x, y and z. But we proved that it is not varying in x direction, it is not varying in y direction, it is varying only in z direction at this particular rate. And therefore, P is a variant only with respect to y. Therefore, we can afford to replace the partial derivative dou by total derivative. So you have dp by dz equal to minus gamma. dp by dz equal to minus gamma. So that's how the partial derivative, we can afford to replace the partial derivative by the total derivative. So the minus sign we have already discussed, it indicates that the pressure intensity P decreases in positive z direction, that is vertical upward direction. So this equation dP by dz equal to minus gamma is the basic differential equation representing variation of pressure intensity, or simply you can call pressure in a fluid at rest. This equation holds good for both compressible and incompressible fluids. So this is applicable for a liquid or a gas. That is, liquids are generally incompressible, because we have discussed that most of the engineering problems we come across in real time are incompressible. So liquids are incompressible, whereas gases are highly compressible. And this equation holds good for both sets of fluids, compressible as well as incompressible fluids. The pressure intensity decreases at the rate of specific weight of fluid with increase in elevation Z. So this is the, or in other words, the pressure intensity increases at the rate of specific weight of fluid in the vertical downward direction. So if you go in the negative direction, that is vertically downward, the fluid pressure increases. So when you go up, you say it is decreasing. When you go down, it is increasing. Now again, let us analyze this equation further. So we have dP by dz, a very simple equation. Sorry. dP by dz equal to minus gamma. When d z equal to 0, then d is equal to dP is equal to 0. What do you mean by this? Now when d is equal to 0, that means dP is equal to 0. What do we mean by this? This shows that the pressure intensity remains constant over any horizontal plane. So if you take a horizontal plane, that is a xy plane, and if you take any point on the plane, the pressure intensity remains constant. It is not varying. So in a horizontal plane, in the xy plane, the pressure intensity does not vary. Now let us integrate this equation. What will we get when we integrate this equation? So you have integral dP by dz is equal to minus integral gamma. So you can write this integral dP is equal to minus integral gamma ds. So integral dP will become P. Now gamma is a constant, the specific weight of fluid is considered a constant, into Ez plus you have a constant of integration minus gamma Ez plus C. This is what we get. So P is the pressure intensity at any point at an elevation Ez in the static mass of fluid. C is a constant of integration. So integration of equation 5 has resulted in the pressure at any point in a fluid at rest. Okay. Now you have to evaluate what is the value of this constant C, then only it is complete. The integration is the solution is complete. Now for evaluating the value of the constant of integration we get, let us consider a liquid of specific weight gamma, which is stored in an open vessel like this, as shown in this figure. This is the free surface. The free surface of the liquid is exposed to atmosphere. So here you have got the atmospheric air. Now the atmospheric pressure acting normal to the free surface, that is, this one is P atmospheric, P small p suffix atm. P atmospheric is referred to like this because atmospheric pressure has got a value. So this atmospheric pressure acts normal to the free surface of liquid because it is under rest, the fluid is under rest or the liquid is under rest, it cannot sustain any shear force. So there is no tangential force acting and only the vertical force that is due to the air column. The atmospheric air is exerting a pressure on the free surface which is normal to the free surface, perpendicular. That will be PA or P atmospheric. Let the height of the free surface of the liquid measured from the bottom of the vessel, it is h. So h is the height of the liquid measured from the bottom of the vessel. So this is the bottom of the vessel. Now the bottom of the vessel is located at a height z0 measured from the datum. So a datum is still taken at a lower level with respect to the bottom. So the bottom of the vessel is located at a height, vertical height Z0 from the datum. Now the height, now Z, how can you refer Z, that is the height of the free surface, Z, or rather, okay, hence the height of the free surface of the liquid from the datum level be Z. Now Z is equal to Z naught plus H, Z equal to, that is Z naught plus H. This is the height of the free surface. So what you can refer, P atmospheric, as you can represent as gamma into Z naught plus H plus C, because it is gamma Z plus C, Z is Z naught plus H in this case. So C is equal to P atmospheric plus gamma into Z naught plus H, you get. So putting the value of C from equation 7, this value into equation 6, we get P is equal to minus gamma Z plus C we had. So C I have replaced as P atmospheric plus specific weight of fluid multiplied by the height of the free surface Z naught plus H. Let us consider a point on the fluid mass located at a depth H from the free liquid surface. That is, we will consider a point here which is located at a depth H from the free liquid surface. The height of the point from the datum level. Now let us express the height of this point from here, from the datum. It is, here the height Z is equal to H plus Z naught minus H. So Z naught plus H, Z naught, this is Z naught plus H minus this H will give you this Z. So you substitute Z by this. So minus gamma into Z is the height of the point which is considered inside the liquid, H plus Z naught minus H plus this one. So when you simplify this, you will get P is equal to the pressure at a point inside the liquid mass at a depth H below the free surface is given by P is equal to PA plus gamma H. So PA is atmospheric pressure plus specific weight of fluid multiplied by the depth of the point below the free surface, depth here. So this equation shows that the pressure at any point in a static mass of liquid depends only upon the vertical depth H of the point below the free surface and the specific weight of the liquid. So this is again another landmark equation which can be conveniently expressed. Instead of expressing it as from the bottom, it is simpler or it is easy to understand, realize when you express it from the top, that is from the free surface. So P is equal to the pressure inside a point or at a point which is inside the liquid mass is PA, that is atmospheric pressure acting on the free surface, plus the product of the specific weight of fluid and the liquid and the depth of the point under consideration. Okay. So we are moving into the last item in this particular module, that is hydrostatic paradox. What is hydrostatic paradox? The pressure at any point in the fluid does not depend upon the shape and size of the container. They do not influence. They do not influence the pressure. What is shape? Size? It does not depend upon the weight of the fluid present. It does not depend upon the weight of the fluid. Pressure depends upon the specific weight of the fluid, not on the weight of the fluid. So let us illustrate this hydrostatic paradox and we will understand what it is by this figure. So I have shown 4 vessels, each having a different shape and also the size is also different. That is, the volume is different, the shapes are different, but each vessel has the same base area. Base area of each vessel is the same. Volumes are different. Say this is vessel 1, 2, 3, 4. V1 is not equal to V2, is not equal to V3, is not equal to V4. Sizes are different. Shapes are different. Shapes are different, evident from the figure. But only thing is, the commonality between the 4 vessels with different shapes and sizes given is they have the same base area. And they have the same liquid of specific weight gamma and also to the same height h. So the height of the free surface from the bottom is same in all these vessels. So same base area, same height, it's everywhere h from the bottom to the free surface. So the free surface in all these vessels, they are in the same plane, horizontal plane. Okay. Now when the liquid contained in a vessel is exposed to atmosphere, the liquid has got a distinct free surface, then the pressure at any point in the liquid is expressed in gauge pressure, that is pressure in excess of atmospheric pressure. That is we derived as P is equal to Pa plus gamma h. So the atmospheric pressure is constant. So let us ignore that. Let us consider only the pressure which is in excess of atmospheric pressure. So when you consider P is equal to gamma h, it is enough if you express like this. We ignore the atmospheric pressure. Atmospheric pressure can be taken as 0, even though it has got strictly it has got a value. Let us consider it as 0 and let us consider only about the pressure which is in excess of the atmospheric pressure or which is below atmospheric pressure. So here when you got a free surface, then when you consider a point below the free surface, the pressure is in excess of atmospheric pressure, that is given by gamma h, where h is the depth of the point below the free surface. So P is equal to gamma h. And in each of these 4 vessels, what is the pressure at the base of the vessel? Is gamma h, because same liquid, or therefore the specific weight is same, the depth of the base of the 4 vessels is the same, so gamma h. So what is the pressure force? The pressure force is pressure intensity multiplied by area. This is Newton per meter square and this is meter square, so you get Newton. So the pressure force acting normal to the base area. So here everywhere the pressure is gamma h and the pressure force is, say, P is equal to P into A, that is gamma h into A, or you can write gamma A h. So as the shapes and sizes of the 4 vessels are different, the volume of liquid is different in each of these 4, in all these 4 vessels. But as each vessel has the same base area and same liquid or specific weight gamma to the same height, the weight of the liquid is, even though the weight of the liquid is different in the 4 vessels because of the different volumes, but the pressure force exerted on the base area of each vessel is the same. Okay, and then so that is called hydrostatic paradox. And pressure head, let us define what is a pressure head, and with this we come to the conclusion of this particular topic, particular module rather. So referring to figure 2, there is this figure, we are considering a point which is at a depth h below the free surface. At a vertical depth h below the free surface, the vertical height h of the free surface of the liquid above the point under consideration is known as pressure head. Say I have a vessel, this is the base of the vessel, this is the free surface. I am considering a point point here which is at a depth h. So what is the pressure at this point? P is equal to gamma h. So the vertical height h of the free surface above the point under consideration is known as the pressure head. That is, pressure head is something like an elevation. So the pressure head is expressed as h is equal to P over gamma. H is equal to P over gamma. So the pressure at any point in a liquid depends upon the height of the free surface of liquid above the point. So the pressure at any point in a liquid depends upon the height of the free surface of liquid above the point. So it is convenient to express fluid pressure at a point in terms of pressure head. So pressure head, the unit is meter. How? P is in Newton per meter square and gamma is in Newton per meter cube. So you have this Newton and this Newton will cancel each other, then you have meter cube by meter square, that is meter. So meter. if you consider two different liquids of specific weights gamma 1 and gamma 2, to exert a pressure of P Newton per meter square at the point, let the pressure head or height of column of liquid required by the two liquids be H1 and H2. So, this I will explain. Say for example, say I have consider two tubes, for example, tubes or glass tubes. So, this is the same diameter and same base area, it is an open tube or a glass container. So, here this is the base. So, I want to express exert a pressure P using two different liquids. The pressure magnitude is known, the pressure intensity is known. So, first I want to use a liquid of specific weight, say gamma 1. In this case I want to use gamma 2. So, I have two glass tubes of same diameter and same base area is same, A, diameter is same. Now, I want to exert a pressure P, that means the pressure force will be P into A, same pressure force, using two different liquids, liquid 1 of specific weight gamma 1, liquid 2 of specific weight gamma 2. So, gamma 1, so P is equal to gamma 1 H1, say it is H1. In another case, a higher specific weight liquid, so the height is say H2. So, P is also equal to gamma 2 H2. So, same pressure, same magnitude of pressure by two different liquids of specific weights gamma 1 and gamma 2. So, the height of the free surface in both the cases will be different, H1 and H2. So, you can equate these two because P is same. So, you have gamma 1 H1 is equal to gamma 2 H2. So, if S1 and S2 are the specific gravities of the two liquids, you can express gamma 1 as S1 into gamma W. So, gamma W is the specific weight of water, that is the standard fluid, and S2 is the specific gravity of the liquid 2 multiplied by gamma W will give you the specific weight of liquid 2. So, you have gamma 2 and gamma 2 will get cancelled with each other. You have S1 H1 equal to S2 H2, S1 H1 equal to S2 H2. So, with this we come to the end of module 1, and then in the coming modules we will discuss on Pascal's law, and then we will work out a few fundamental problems involving pressure head and pressure intensity. Then also we will then go into the different types of manometers, how the manometers can be used to measure pressures at points in fluid flow or in a static fluid system. And then we will also work out a few problems asked in the competitive examinations like GATE and UPSC. So, with this, thank you very much. Have a good day.